Hi, this is our ME452 final presentation for the analysis and redesign of a can opener. So can openers provide an easy way for people to open cans without a pull tab. They have a knob that can be turned by hand that spins a set of gears, and on one side, a knurled disc moves relative to the can opener, and the other side, the cutting disc cuts through the metal top of the can. So in 1972, there was estimated to be 6.8 million can opener units sold, and we know that number is likely much higher as of today. Our research shows that the market for can openers has a compound annual growth rate of 7.99% as of the year 2021, so the market is continuing to grow. The primary customers here are home kitchens. These are people that need to open cans in their home. They use the can openers relatively light use, and they don't need to rebuy the product very often. While the secondary customers are commercial kitchens, they have a much heavier use of these products and will sometimes also buy electric can openers because they're required to open the cans at a faster rate.
Yeah, so here's our exploded CAD, fit with all these sub assemblies for a can opener. It's a very standard can opener that's widely used. So now we have our fast diagram. So right away we have the important function is that it can open cans, and then for functionality that it has to cut the can, so it needs to both pierce the can, affix the can, things like that. And of course we have more intangible requirements for our can opener, like pleasing the senses, assuring dependability, convenience, and enhancing the product.
Here we have our functional component mapping matrix where we map the components of the can opener to the components found on the FAST diagram. Here we have our quad chart classification. Most of the components, as you can see, fall under high importance while being split between high assembly cost, manufacturing costs, and low cost. Here's a fully assembled view of our can opener. And here's our functional differentiation table, splitting the different functions and components between common functions, differentiated functions, platform components, and then modules.
So for our product family design, we've opted to make a second or a different crank handle, one that uses more of an arm motion instead of simply a wrist motion by the use of this kind of larger knob. It uses the same modular interface on the pin, which is sort of like this T-shaped pin that turns when you turn the either the twist knob or the crank handle. And we've revised the product family assembly diagram to differentiate. So this is the old one where it would put the knob on first and then it would join the two handles together. We've delayed the differentiation to be last, so now it joins the handles and then adds the twist knob on top.
In our redesign for manual assembly, we decided to redesign for our platform redesign the crank handle and twist wing pin assembly step, and for our module part, we decided to redesign our main pivot pin and upper and lower frame pivot assembly step. These were chosen based off of their higher assembly times and also align with our quad chart. They also align with our function component mapping matrix, in which these parts align with parts that have many functions. For example, the crank handle has 3 functions and other parts have 2 functions, which are 2 or 3 functions are the highest number of functions in our function component mapping matrix. The first part we redesigned was the pivot pin, where we removed the main pivot pin and redesigned the upper and lower frames in order to have a snap fit, utilizing DFA principles 1, 2, and 3, reducing part count, reducing fasteners, and implementing a snap fit. Our other redesign assembly step along the crank handle involved redesigning the twist wing pin, adding a locator nub to add this feature to facilitate part orientation, avoid tangling and nesting, and allow for easy insertion. All of these changes reduced our assembly time by 12.13 seconds, or 20% overall, did not have an impact on part function, and reduced cost by about 5 cents by removing the main pivot pin.
The crank handle is intended to be made out of rubber and has a few different processes that can allow us to fulfill all of its requirements. We have machining, injection molding, and compression molding. We finally chose injection molding because it allowed us to create the shape needed with the tolerance and surface roughness required, but it also had the best economic batch size.
So when designing for manufacturing, the first part of our product that we decided to redesign was the crank handle. So it has a wall thickness of 0.25, but it's not uniform all the way around. And after calculating the total manufacturing cost, we got it to be 63 cents per part. And on the right side, you can see DfM Pro showing us some of the recommendations for redesigning this part. And so after redesigning, we did this by reducing the wall thickness and making it a uniform wall thickness while also avoiding sharp corners. After redesigning, our total manufacturing cost is 54 cents without changing any of the major dimensions. And with doing this, we saved 9 cents per part with no change to the product function and no change to the assembly cost.
So yeah, next we have our process selection handle grip. Again, we went with injection molding due to the material. And out of the three possibilities, we felt that injection molding was the most reasonable because of the price that it would cost to do it versus things like machining or compression molding. Yeah, so next we have the handle grip. So just right away, the original handle grip has a wall thickness of around 1.5 centimeters. So it's pretty thick. And then we just have our typical slot that the blade can slide it, or the metal part of the camera can slide into. And here this is costing around $1.22 with injection molding, which we picked. And as you can see on the right, we have our DfM Pro analysis, and it gave us a couple recommendations. One was the angle of the slot we had, and then the other was wanting uniformity of the thickness. So next we have our other design, and as you can see here, it's largely similar dimensions. So we kept the length and width largely the same. But what you'll notice is we took out a lot of the volume in the handle, and we also made the thickness uniform. So rather than 1.43 centimeters of thickness, we have it now as 0.25 centimeters of thickness. And with the decreased material cost and the uniform thickness, as well as changing the angle, we were able to cut our total cost to 96 cents, which is a 26-cent saving per part. And this does not affect the product function or the assembly cost at all. And next, we just have some critical dimensions. And what you'll notice is the critical dimensions largely will stay the same after the changes.
Let's go over the process selection for this new part that combines the can cutting blade, a pin clip, and a spacer. This new can cutting blade needs to be made out of steel, has an interesting 3D solid shape, and needs a pretty good tolerance. We looked over a few different processes that could fulfill this criteria, and we finally settled down machining because it gave us all of our requirements. The tolerance can be achieved by a standard 3-axis mill, and it gives us that pretty smooth surface as needed for a blade.
Here we pick the sub-assembly for the upper arm for automated assembly. This is the before image with the components picked and the cost shown. After updating the assembly, parts 2, 9, and 10 were combined as they had similar functions, and also got added features for better alignment. This overall reduced the assembly costs. However, increased manufacturing costs in the gear components as an extra feature was added, and also introduced a new combined part that had a higher assembly cost or higher manufacturing cost.
And so for our product service system, we've decided to go for a refurbish and recycle program for commercial kitchens. So basically, the refurbishment service will kind of replace can openers that are in commercial kitchens, every quarter or so, or kind of however often they need to be replaced. And then refurbish these, the cutting discs, clean them up, things like that, so that they can be put back into service. And once they've reached the end of service, they can be removed as part of our recycling program. Additionally, we'll be making sure that the metal that's used to make them can be recycled, and that we can use thermoplastics for the injection molded parts as they can be kind of remelted. And then we can't do this part yet, but
Okay, sounds good.